So we're still trying to do the same thing as we did in the simple linear regression model. We're still trying to minimize the sum of squared residuals, okay? So if we think about the simple regression not simple, but a multiple linear regression case, we can choose to minimize the sum of squared residuals with respect to these estimators, beta naught hat, beta 1 hat, and beta 2 hat, if we had just two independent variables, x1 and x2. Okay, so you can extend this model for the k independent variables case very easily, where we have, again, we are minimizing the sum of squared residuals, but we have many more variables. So we have k variables, k independent variables, and k plus 1 estimators as a result, including the intercept. So we can use a multivariable calculus, right? Take first order conditions with respect to these unknowns. Because we have k plus 1 linear equations and k plus 1 unknowns, we can solve this. And usually the software does that for you. But basically, if you want to look at it, if you start taking the first order conditions, you would find from that minimizing sum of squared residuals, we get all of these conditions, okay? And we can solve for our estimators using this system of equations. So once we have these conditions, we can get our unique solutions, and usually softwares like Stata or Python, all of these different softwares can find that for you. Ultimately, what we want is, remember, we want that if we have x and y, and we have all these points, and we have a bunch of other x's, we're trying to fit the best line through this. So what the computer is trying to do is it's trying to come up with different lines and seeing which of these lines, which of these rotations best fits the data. And by best fit, we mean by which line minimizes the sum of squared residuals, okay? So once we have that regression line, once you have your estimates, you can actually predict y, which is your dependent variable of interest, which is your variable of interest that you're trying to explain, using these estimators, right? So you've got some estimators or coefficients, and you could take a bunch of values for x1 through xk and come up with some sort of an average prediction for this dependent variable. That's what we're trying to do. Okay, so typically you would find in the book and even in my lectures that we will replace y by what the dependent variable actually is, right? In the example with the final scores as a function of missed lectures, we basically said that we're trying to say final score equals beta naught hat plus beta 1 hat missed lectures plus beta 2 hat prior GPA. So we are going to then replace y with final and the x's with what those variables actually are. Okay, so it's important to remember how are we interpreting our slope coefficients of interest, okay? So remember that if we had two independent variables, those have ceteris paribus interpretation. So let's say this was our model, and y hat, let's write this down. So let's say this was final. You are trying to predict the final score based on your model. And this is missed lectures plus beta 2 hat prior GPA. We can then say that the change in y hat is a function of, or can be written out as beta 1 hat times change in x1 plus beta hat 2 change in x2, okay? And we can take this and try to make sense of what the beta 1 hat and beta 2 hat estimators are. So here, if you take the partial derivative of the dependent variable final, right, that you're trying to predict with respect to missed lectures, this is equal to beta 1 hat, right? So this is basically saying this is a partial derivative, which means that we are assuming that x2 is equal to, change in x2 is equal to 0, right? So we're saying holding prior GPA constant. If prior GPA is constant, right, we take two individuals and we say that if there is person A and person B, and these are the only two people in our sample, and let's say their prior GPA was 3.5, we are holding their prior GPA constant, and the only thing that's allowed to change is how many lectures they missed. So there's some variation in the missed lectures, and we're saying what is the average prediction for that final exam score if we held everything else constant but only allowed the missed lectures to change, okay? That's the interpretation of this beta 1 hat, okay? So remember, it is a ceteris paribus interpretation always. So ceteris paribus interpretation. And the nice thing about regression analysis is that we don't really have to find two people in our sample who have this. So regression analysis, the interpretation is such that we can hold that constant. Okay, so this may not be true in the sample, but the interpretation is such that we're holding everything else constant. Okay, so again, these are partial effects. The slope coefficients are capturing partial or ceteris paribus effects. And so we can say that beta naught hat, beta 1 hat through beta 1 hat k are the OLS estimates from the regression of y on a bunch of x's, right? Or of yi on a bunch of xi1, xi2, xik for n cross-sectional units if we want to emphasize that our sample size is n.